Section 5.4 is about how eigenvectors are related to linear transformations. So what we're going to look at in section 5.4 is the idea of linear transformations, and specifically a matrix for a linear transformation. All right. So basically, each linear transformation from one vector space to another, so our transformation is labeled as T, from vector space V to vector space W, can be written as a matrix multiplication problem for coordinate vectors given that we know some bases for V and some basis for W. So we set out with a basis for V, a basis for W, and no matter what our vector spaces are, those coordinate vectors are in fact from Rn. So we can think of it as matrix multiplication as long as we're using the coordinate vectors. All right. So labels there, we're going to have V, our domain vector space, have basis B, and W, our codomain vector space, to have basis C. So basically, we start with a vector in our vector space. We're going to write it as a coordinate vector. That way it's in Rn for some n. And then we're going to multiply by some matrix that represents T. And this should end up in some other Rm and that will represent a coordinate vector for the T of x, the image under the transformation. Now, one thing you'll notice here, we're going to always use finite dimension vector spaces. That's because when you get into the infinite dimensional vector spaces, the matrix would have to be an infinite dimensional matrix. So we obviously don't do that. But for finite dimensional vector spaces, this will always work. We can take any finite dimensional vector space V. We can write the coordinate vector as some Rn, multiplied by the matrix that represents T. That gives us out a C coordinate vector, which is the image of x after we've taken their transformation. Now, if you think about this, what we're actually doing is we're taking our vector x, let me rewrite that, I'm sorry. So taking our vector x, I don't want to draw that because that looks a little bit bad when I draw with my mouse. All right, so we got here, we took our vector x. Normally, we just apply the transformation to it, and we get T of x. Now, this x can be from any vector space V, and our image can be from inside of any other vector space W. Now, we hopefully, probably, feel most comfortable dealing in Rn. So what we do is we transform this x from a vector space V into the coordinate vector for x relative to some basis B. That way we're inside of Rn. We can take this transformation, we can write it as a matrix multiplication problem, multiply this thing in Rn by a matrix, and get out the image of x with respect to basis C after we've hit it by the transformation. Okay? So basically, this just takes us from any vector space that we want. Again, we're using finite dimensions to using Rn. Okay? So, by the way, writing the x to b is going to be a straightforward process. We've seen that be done before. This section is looking at how do I take this transformation and associate some matrix to it. Okay, so it's going to be this diagram, and basically these are just parallel ideas that we take some x, we hit it with the transformation, and we get some image of x. Now we're going to take, and instead of, we're going to set up an x, and we're going to create some sort of, that's better, image there, multiply by a matrix. I'm going to know how to multiply by the matrix as we see here in a little bit. That'll give me the image of t of x, and these things you can actually go back and forth between, right? Now mostly we're going to be going down this side, over, and then back up, but that's the idea. All right, so hopefully that all makes sense. And that's better than me drawing all those letters. Okay, so let's create the matrix that represents the transformation. Okay, so here's how we do it. It is a linear transformation. So what does that mean? That means if I take an arbitrary vector x from our vector space, and I write it as a linear combination of the basis elements, then x written as the coordinate vector corresponding to those basis elements will just be the coefficients of those basis elements. In this case, I have 3 basis vectors, and therefore my coordinates are going to have 3 entries, which we call A1, A2, A3. Now, recall what's going to happen. Since my transformation is linear, if I apply this transformation to the vector x, then what's going to happen is I'm going to apply the transformation to the whole thing. Because it's linear, I can split up, I can apply the transformation to each part. Since it's linear, I can sort of factor out those coefficients, A1, A2, and A3. So because it's linear, I can apply the transformation to each of these 3 pieces, each of these 3 terms, if you will, and then I can sort of factor outside that transformation that constant A1, A2, and A3. Now what this should tell you is that the columns of M are going to correspond to the images of where my transformation sends a basis element, especially the basis elements for basis B. So if I'm going to take and multiply by a matrix multiplication M times A1, A2, A3, it's going to correspond to, the columns are going to be essentially what happens to my to the basis elements under my transformation. So the matrix has to be where these basis elements go under the transformation, written with respect to basis C. Okay. This matrix M is called the matrix for the transformation relative to bases B and C. So the matrix relative to basis B and C. Let me give you an example of what this looks like. So let's find a matrix that would correspond to the transformation here. So we're going to let B as a basis consist of 2 elements, B1 and B2. And we're going to let C as a basis consist of 3 elements, C1, C2, C3. Now, vector space B is going to correspond to V. I'm sorry, basis B is going to correspond to vector space V, and basis C is going to correspond to vector space W. And let's assume the transformation is linear. It goes from V to W, such that if you put in B1 into the transformation, it gives me out 2C1 plus 4C2 minus 1C3. And if I put B2 into the transformation, it spits out negative 4 times C1 plus 9 times C3. Okay? Hopefully that all makes sense. Let's find a matrix for T relative to bases B and C. All right, so let's go back to this picture that we had earlier. We have vector elements, and we want to figure out, we know what the transformation does to the basis elements. So if I know what the transformation does to the basis elements, I know what it does to all the elements, okay? So my first step is going to be writing the basis elements relative to basis B, all right? So here's what our transformation does. It takes B1 and spits out 2C1 plus 4C2 minus 1C3. Now, what is my basis element number 1 with respect to basis B? Well, it's 1, 0, because if you wrote this as a linear combination, maybe this makes it a little bit, B1 would have to be 1 times B1 plus 0 times B2, right? So as with respect to basis B, my basis element is 1, 0. Similarly, my basis element B2 is 0, 1. Now, what should the transformation do to B1? Well, it does this. So what should my matrix M do to this coordinate vector? Well, it should spit out, whoops, my apologies. Keep hitting bad stuff here today. It should spit out 2, 4, negative 1. 2, 4, negative 1. Because what that is that is the image of B1 relative to basis C. Okay? And if we're doing this, we could do a similar argument with element B2. My matrix should take element B2, and it should spit out negative 4, 0, 9. Oops. Because that's what the image of B2 goes to relative to basis C, negative 409. Okay? Now that we know what our matrix does to 1, 0, and what our matrix does to 0, 1, we should be able to just spit out what that matrix is. And if you think about it, this matrix is hopefully easier than writing down a whole lot. We need it to, when it multiplies times the vector 1, 0, We need it so that it multiplies vector 1, 0 and gives me out 2, 4, negative 1. That just means my first column needs to be 2, 4, negative 1. And then we need it to multiply by 0, 1. And give me out a negative 4, 0, 9. And therefore, this matrix M is going to be the one we need to multiply by to go from elements with respect to basis B to elements, coordinate vectors with respect to basis B, and transform them into coordinate vectors with respect to basis C. So there you go. That is the matrix that we need. All right. 2, 4, negative 1, negative 4, 0, 0, 9 in columns. All right. So I'd like you to take just a moment and do the same thing, but I'm sure you can do it quicker now, corresponding to this transformation. In this case, we have 3 basis elements from basis B and 2 basis elements from basis C. Once again, we're going to go from V to W. So push pause on the video and create the matrix T. All right, so hopefully you went ahead and did that. We wanted to find the matrix for T relative to bases B and C. By the way, these must be different vector spaces, V and W, than we had in our last example, because in our last example, V was a two-dimensional vector space because it only had two basis elements creating it. And W was a three-dimensional vector space. So we must have had different V's and different W's here because V now is three-dimensional, W is two-dimensional. All right. So what we have, as you can see, B1 goes to C1 plus 8C2, B2 goes to 5C1 plus 4C2, B3 goes to 6C1 minus 5C2. You follow what happened with the last one. All we're going to do, I don't have to do a lot of things, but all I have to do is realize that these coefficients of C's are going to create the columns for my matrix M. And my matrix M is the matrix for T relative to basis B and C. So we'll see in the first column, we're going to get a 1, 8. In the second column, we're going to get a 5, 4. And in the third column, we're going to get a 6, negative 5. So when you create your matrix M, again, M is the matrix for T relative to bases B and C. We get 1, 8, 5, 4, 6, negative 5. So that should be your matrix M. All right. Let's do one more of those. I want you to go from a three-dimensional vector space V to another three-dimensional vector space C and find the matrix for T relative to the bases B and C. All right, so hopefully you went ahead and did that. If you didn't, push pause because I'm going to reveal the answer. So in column 1, we're going to get 5, 0, negative 6. In column 2, we're going to get 2, 8, 1. And in column 3, I'm going to get 2, 10, negative 2. So I'm going to end up with this matrix 5, 0, negative 6. Let me make sure, yep, 2, 8, 1, 2, 10, negative 2. So those are my columns for my matrix M. All right, and that matrix is the matrix that represents the transformation T with respect to bases B and C. So there we go. Now, obviously, we're not just going to give you an arbitrary basis B and an arbitrary basis C. We're going to basis B and basis C. We're going to give you specific transformations and specific vector spaces. And where this stuff gets really useful is when you're dealing with like polynomial vector spaces or non-Rn vector spaces. Because when you're dealing with polynomial vector spaces, what this will do is it'll allow us to use Rn, which is really nice because Rn is really easy to calculate with, whereas polynomial vector spaces aren't as easy to calculate with. So let's define a transformation from polynomials of degree 2 to R2 by the following. Take this polynomial, and in the first entry, we're going to plug in 3. In the second entry, we're going to plug in 2. So polynomials of degree 2 and less to R2 by this. Okay? Now, let's just try to understand what this transformation is doing and how to calculate with it. We've dealt with one similarly earlier in the class, but I want to refresh your memory about that before we move on. So I want you to try to calculate what this does, what this transformation would do to x squared plus 4x minus 10. And then figure out what this transformation would do to 6x plus 4. Push pause and see if you can do that. If you've forgotten, then just wait a couple of seconds and we'll start going there. All right, so if you don't remember what this did, let's go over it. So we have this transformation that takes a polynomial, and in the first entry it plugs in 3, and in the second entry it plugs in 2. Now when I say plug in 2, I mean into the polynomial itself. So when I plug in 3 into this polynomial itself, what we're going to get is we're going to get 3 squared plus 4 times 3 minus 10 into this polynomial. And then the second entry obviously is plug in 2, so take 2 squared plus 4 times 2 minus 10. And what we see is that in the first entry, this is going to be 9 plus 12 minus 10, which gives you an 11. Then you get 4 plus 8 minus 10, which gives you a 2. So you get 11, 2 out of that. Okay? Now, what's going to happen when you take a polynomial 6x plus 4? Well, if you haven't figured it out, you push pause and go through it. Otherwise, I'm going to go through it right now. When you plug in 3, you get 6 times 3 plus 4. When you plug in 2, you get 6 times 2 plus 4. So what do we get? Whoops. Well, when I plug in 3, I got a 22. When I plugged in 2, I got a 16. Hopefully I've done my calculations right. Obviously, double check those in case I've messed that up. But that's what I got on my calculations. So when I take this transformation, I'm getting out a vector from R2. So I'm taking a polynomial, transforming it, getting out a vector from R2. And again, double check on my calculations. I just did those quickly in my head. So, so this is a kind of a unique transformation. Let's try to take a basis for P2, polynomials of degree 2 and less, and the standard basis for R2, and create a matrix for this transformation using x squared, x1 as the basis for polynomials of degree 2 and less, and the standard basis for R2. Okay? If you can do it, push pause and do it. Otherwise, we'll go through the whole thing in just a moment. All right, so let's go ahead and do that. So here we go. Take our elements from polynomials of degree 2 or less and send them over to R2. Now this is what we're going to use for our basis for polynomials of degree 2 or less. There's x squared, x1, and standard basis for R2. So in my previous notation, the script B basis would have been x squared, x1, and standard basis would have been the script C basis. So all I have to do is see what happens to T of each of my basis polynomials. Okay? So what's going to happen when I take my x squared? Again, that x is just the variable x. That's not a vector. So it's a variable x, x squared, and plug in 3 and plug in 2. Well, when I plug in 3, I get 3 squared, which is 9. When I plug in 2, I get a 4. There we go. What's going to happen when I plug in my variable x and see where that takes my transformations? Well, transformation, plug in 3, you get a 3. Plug in 2, you get a 2. Hopefully everybody sees what I'm doing. I'm just plugging into this variable here, plugging into that variable there. Now what's going to happen when it's a transformation of the constant 1? Well, you plug in 3 into this polynomial, and there's nothing to plug it into. You just end up with 1. Plug in 2 into that polynomial, just end up with 1. So notice that these vectors are the vectors under my standard basis. That's the nice thing about using the standard basis, that every time 9, 4 is in fact, let me just write it this way. 9, 4 with respect to basis C is in fact just 9, 4. Okay, so that's why we like using the standard basis. Right? It's just 9 times this first one, 4 times this second one, add them up. Okay, so we get 9, 4, 3, 2, 1, 1. And what that means for our matrix, that means that my matrix, which we've been calling M, is going to be a matrix which looks like this. 9, 4 as my first column, 3, 2 as my second column, and 1, 1 as my third column. So 9, 3, 1, 4, 2, 1. All right, that's the matrix M. Now that is, in essence, the matrix that describes the transformation using the coordinate vectors for B and coordinate vectors for C. So what I would like you to do is just think about what would have happened if we reversed the order of the basis for P2. So instead of starting with x squared as the first basis element, what would have happened if we started with 1 as the first basis element? Now, this shouldn't be a big surprise to anyone. Whoops. What really is going on? So all we did, switch the order. That's not going to change what the transformation does to these three basis elements. All it's going to do is change the order of the columns of my matrix. So I'm going to now go from 9, 4 in the first column to 9, 4 in the third column. All right. So in some regards, this matrix is also dependent upon the order in which you write your basis. If I write it as 1x, x squared, it's going to be different ordered columns than if I wrote it x squared, x1. Okay? Again, even though the transformation does the exact same thing, the order of the basis elements is important. Okay, that's one little unique thing that you need to pay attention to is the order of these things. And especially when you're doing your homework online, order is important. So be aware of that. So be aware that we get things in the right columns. But whichever basis you pick, you're going to get a matrix, and that matrix is going to be representative of the transformation from with respect to B and C. All right, what I'd like you to do is I would like you to push pause on the video and try this one. We're going to take and find a matrix for the transformation using the basis 1x, x squared for polynomials of degree 2 and less, and the standard basis for R3. And I want you to come up with the matrix for this transformation from this basis to the standard basis with respect to basis B and the standard basis. All right, so hopefully you went ahead and did that. So we're plugging in 2 for the first entry, -1 for the second, and 0 for the third entry. All right. Now, let's start here. So we're taking our basis, 1x, x squared, and we're sending it to something that is going to be written with respect to the standard basis. Standard basis, remember we call these E1, E2, and E3. So if I mention that, that's what we're going to be doing. So let's start with 1. So if I take 1 and transform it, plug in 2, should be fairly obvious what 1 does. You plug in 2, you get a 1. You plug in -1, you get a 1. You plug in 0, you end up with a 1. So 1 gets sent to 1, 1, 1. Okay? How about x? Well, x is going to be sent, plug in 2, you get a 2. Plug in -1, you get a -1. Plug in 0, you end up with 0. So 2, -1, 0 when I plug in x. When I plug in the polynomial x squared, I end up with, well, x squared, plug in 2, you should end up with a 4. When you plug in -1, you should end up with a 1. When you plug in 0, you should end up with 0. Now I go to double check what order my basis was in, and I see, oh yeah, my order was 1 and then x squared. So I go 1, 1, 1. That'll be my first column in my matrix. Then my second column is 2, -1, 0. And then my third column is going to be 4, 1, 0. And there you have it. This matrix is the matrix for transformation T with respect to bases B and C. And by the way, again, don't forget what we're doing. That diagram, here we were dealing with polynomials of degree 2 and less. We said it's easier if we write those, if we see what happens to those with respect to basis B. Since now I know what that's going to look like, I can figure out my matrix by saying what does each basis element have as its image. And so we kind of go back and forth using this, these parallel diagrams. All right, so there you go. Hopefully that all makes sense. Now for these first few examples, we've always went from and to different vector spaces, like polynomials of degree 2 is a different vector space than R3, although there's a mapping back and forth to it. Or we went from polynomials of degree 2 to R2, you know, those types of things. Or we went from some sort of arbitrary vector space to an arbitrary vector space. But what if the vector spaces are the same? And what if we were willing to use the same matrix, or same basis, okay? So when we do a transformation from a vector space to itself, then we can use the same basis for both B and C. So for both our originating vector space and our ending vector space, we can use the same basis. Now, nothing really changes. Remember the matrix we used before? We said, well, the columns were going to be our basis elements the image of my basis elements with respect to basis C. So now it's just going to be the image of my basis elements with respect to basis C. So the matrix we were calling it the matrix for transformation T relative to bases B and C. Well, now if we go to the same from and to the same vector space, and we use the same basis, we just call it the matrix for our transformation T relative to basis B. So if we're going to use relative to basis B, that just means we're using the same basis for the domain and the codomain. And sometimes this is called the B matrix for T, matrix for T relative to B, the B matrix for T. Often it's denoted as my transformation with respect to basis B. So sometimes I'll say that, transformation with respect to basis B. And what this allows us to do is go from like polynomials of degree 2 to polynomials of degree 2 using the basis 1x squared, just like we did before. And now we can say, well, what's going to happen with our transformation? How are we going to write a transformation which does this? It takes an arbitrary polynomial, which looks like a1 as a constant, plus a2 times x, plus a3 x squared, and sends it to this constant, 2a2 minus 5a3, plus the coefficient of x is 4a1, and the coefficient of x squared is 6a1 plus 7a2. All right? Now, I want you to go ahead and try to figure out what this is going to do. And once you figure out what this is going to do, try to figure out what it does to each basis element. Try to come up with the matrix for the transformation relative to B, or the B matrix for T. All right, so hopefully you went ahead and did that. So we take our transformation and we say, what is our transformation to do to my basis elements? 1. What does it do to x? What does it do to x squared? Now, think about what's going to happen when you plug in 1. Basically, the a1 is going to turn into a 1, a2 and a3 are going to be 0. So we're going to get 2 times, this is going to go to 0, this is going to go to 0, this is going to be a 1, so you're going to get 4x plus a1 is going to be a 1, a2 is going to be 0, so you get 4x plus 6x squared. So there you go. In a similar way, when you plug in x, what's going to happen is a1 and a3 are going to be 0. So anytime you see an a3, anytime you see an a1, it's going to be 0. And anytime you see an a2, it's going to be the number 1. So you go 2 plus 7x squared. So 2 plus 7x squared, that's what you get when you plug in an x. When you plug in an x squared, a3 is 1, a1 and a2 are both 0. So you get a negative 5. A times a3 is going to be negative 5. And then everything else is a 0. So you just get negative 5. Now think about what this means. Because my basis was ordered as 1x, x squared, when you write your matrix, the 1 as a coordinate vector with respect to my basis is going to have a 1 in the 1 entry. Let me write that down. So this is what I mean. So my matrix 1, because of the order, it's going to go 1, 0, 0. Because my basis started as a 1 was the first element of my basis, and x was the second element of my basis. X squared was the third element of my basis. So I've done that. Well, what does the image look like? It looks like 0, 4, 6. And again, that is with respect to the order of my basis. So the 1, the x squared. Okay? And in a similar way, we're going to do the same thing with x. We're going to get 0, 1, 0 is 2, 0, 7. And then similar with x squared is going to be 0, 0, 1. It would be equal to negative 5, 0, 0. So what that means for my matrix M, my matrix for T relative to the basis B, is the first column is going to be 0, 4, 6. My second column is going to be 2, 0, 7. And my third and final column will be negative 5, 0, 0. And there you go. And why that's nice is because now we have a transformation, a matrix multiplication transformation from R3 to R3 that represents a transformation from polynomials of degree 2 to other polynomials of degree 2, or to polynomials of degree 2. And when we utilize this line, this matrix multiplication is something that we can program into a computer much, much easier than dealing with polynomials of degree 2 to polynomials of degree 2. And this trick works no matter what vector spaces V and W are, as long as they are of finite dimensions. Okay. Now I want you to do one more like that, again from polynomials of degree 2 to polynomials of degree 2. See if you can get this one fairly quickly. Push pause on the video. So here is that transformation, and let's go take to it. So if I plug in a 1, I get 1 3x. So I get a 1 plus 3x, and that's it. There's no A1 down here. Again, when I say plug in a 1, I'm saying A1 is 1, A2 and A3 must be 0. When you plug in the x, A1 is 0, A2 is 1, A3 is 0. So we're going to get negative 4 minus 3x plus 8x squared. And then when I plug in the x squared, that's a 0 for A1, a 0 for A2, and a 1 for A3. So I get 1. There's no coefficient for x. And I'm going to get negative 1x squared. So there you go. So 1 goes to 1, 3, 0 in terms of coordinate matrix. That first column is going to be a 1, 3, 0. I don't know what these are going to be yet, so I should probably erase them. All right, that's better. So 1, 3, 0. As far as x goes, it's sent to negative 4, negative 3, 8. Okay. And x squared is sent to 1, 0, negative 1. There we go. So that is the matrix for my transformation relative to basis B. And again, basis B was 1x, x squared. Oftentimes, by the way, just as a side note, this is called the standard basis for polynomials of degree 2. And polynomials of degree 3, sometimes they say the standard basis is 1x, x squared, x to the third. So sometimes you'll hear that language. I've just been calling it this basis. And with the standard basis, I'm always generally talking about Rn. So there we go. Now things can get a little bit more complex when we're dealing with, instead of giving you a transformation and giving you the sort of outputs, what if I gave you the transformation as a matrix transformation to start with? So here we have a transformation T. It's a linear transformation, and it's defined by a matrix transformation. 3, 4, 2, negative 3. So it goes from R2 to R2. And we want to find the B matrix of T with respect to basis 2, 1, and 0, -1. Now we know how to do this. Hopefully we know how to do this. We see what this transformation does to each of my basis elements, and then we sort of map it back. So if you want to, I want you to see what this matrix does to each of these basis elements, and realize that when you're multiplying A times a basis element, you're doing so in the standard basis. So we're going to have to convert whatever the outcome is into our basis B. I'll talk about that in a second, but I want you to just take a moment, push pause on the video, and see what this linear transformation does to 2, 1, and then see what this linear transformation does to 0, -1. All right, so let's think through this. What is going to happen to 2, 1, and 0, -1? So take this matrix A. The transformation is defined by just multiplying A times any vector. So let's take that matrix 3, 4, 2, -3 and multiply it times the vector 2, 1. So 3 times 2 is 6, plus 4 times 1 is 4, so 6 plus 4 is 10. All right, hopefully I didn't do that too quickly. You can always use your calculator as well. 2, -3 times 2, 1. 2 times 2 is 4. -3 times 1 is -3. 4 plus -3 is a positive 1. So I got the vector 10, 1. Now, this is just the vector 10, 1. This is not the this is not written as a linear combination of these vectors. This is just sort of the standard vector 10, 1. Okay? If you think about it, what I've done is I've basically just went from here, this part of the diagram, to over here, this part of the diagram. Okay? So if I want to find my matrix, I need to figure out what that is here. How can I write this vector, which is 10, 1, as a vector with respect to my basis, which in my case is basis B? All right, so I need to write it with respect to basis B. So what I need to do is I need to think of what linear combination, what coefficients, how could I take 10, 1 and write it as a sum of the vectors 2, 1 and 0, -1? Well, pretty easy that the top entry has to be a 10, so that means 2, 1 would have had to have been multiplied by a 5. And if the 2, 1 is multiplied by a 5, 5 times 1, I need this to be multiplied by a 4. So what I'm saying here is that this matrix times 2, 1, let me do something real quick. So let's write it this way. This matrix times 2, 1, written with respect to basis B, would have had to have been equal to 5, 4. So with respect to basis B, the matrix that I am going to use is going to have first column of 5, 4. Now we're going to do that with 0, -1 as well. Okay, so matrix times 0, -1 is actually the matrix. Well, now that I've forgotten how to do it. So 0, -1. So 3 times 0, 4 times -1. We got a -4 in the first entry. 2 times 0, -3 times is a +3 in the, so you're getting -4 in the first entry and a +3 in the second entry. Now, if you wanted to write that as a linear combination of 2, 1 and 0, -1, think about this. Top entry needs to be a -4, so you're going to take that times a -2, and then -2 plus what? So you think you get a -5 there. Whoops. A -5 there. Okay, let me check my maths there. Check my math there. -2 minus 5 times -1 is a 3. -2 times 2 is 4. Plus 0 is -4. Okay, so I got -4 and I got a 3. So there you go. And what we're saying is that if you take 0, -1, multiply it times the matrix, and write the coordinate vector with respect to basis B, you get -2, -5. Okay, so what would my matrix M be? Well, my matrix M would have been a 2 by 2 matrix whose first column is 5, 4, and whose second column is -2, -5. And that would be the transformation with respect to basis, the matrix for the transformation with respect to basis B, all right, or the B transformation matrix for T. Okay. Now, what that is doing, that's kind of a long way to go about this, right? We kind of went from here, did our transformation, went to here, and then went down this way. In other words, if I'm doing this, I found this way, and then I went down to there, and then that allowed me to find my matrix because this is a pretty easy, went down to there, and then I kind of found my matrix that way. Okay, so went over and down and then back to find my matrix in some sense. Okay, so you might say, well, that was a lot of work. Why would I ever want to do that? And I hope that you're thinking that right now. Let's see if the next example can shed some light on why we would want to write our matrix with respect to a different basis. So I want you to write this matrix, 2, 3, 5, 4, and this basis, -2, 2, 3, 5. I want you to write the B matrix transformation of T, so the B matrix of T, with respect to this basis here. Push pause on the video and go ahead and try to do that. All right, hopefully you went ahead and did that and notice something very interesting. So let me go through this. A is this matrix, 2, 3, 5, 4. My matrix B is negative 2, 2 as my first vector, 3, 5 as my second vector. So when I take my matrix A and multiply it times negative 2, 2, I get actually 2, negative 2. In other words, that's just negative 1 times negative 2, 2. And so if I was going to write that as a linear combination of these two basis elements, it'd be negative 1 times negative 2, 2, and 0 times 3, 5. Now, what that means is, in short, negative 2, 2 is an eigenvector for this matrix, which had eigenvalue of negative 1. So when I take my matrix and I multiply it times that eigenvector, we get the eigenvalue of negative 1 in the 1, 1 entry, and then a 0 in the 2, 1 entry. Now, when you go ahead and do that for 3, 5, you'll notice that 3, 5 is also an eigenvector. This time, the eigenvalue is a 7. So you go through all the work, A times 3, 5 is a 21, 35, which is 7 times my vector 3, 5. So if I'm writing it as a linear combination of the two basis elements, it's 0 times this vector plus 7 times 3, 5. So when I write my image with respect to basis B, it looks like 0, 7. So my matrix, which is my B matrix for my transformation, is actually a diagonal matrix. It's the diagonal matrix with negative 1, 7 on the diagonal. And we saw in the last section how nice it is to have diagonal matrices, to be dealing with diagonal matrices. A lot of times that makes our calculations easier. A lot of times it just makes our life a lot easier to deal with, especially when we're dealing with computer programming. So a lot of times it's easier if we can find the right basis. It's easier to change everything into a basis. Do all of my matrix multiplications, which are diagonal, which is, diagonal matrix multiplications, and then change it back into my original form, than it would be to be able to do the transformation by itself. So a lot of times this saves us a lot of calculations going this way if we know that our matrix is diagonal. Okay? Hopefully that makes sense to you. Sorry. So getting back to the thing we did, what we said is, okay, now instead of avoiding the A might be a complicated calculation process. How does that relate to the diagonal matrix? Well, our matrix here, my matrix multiplication, I changed that to a D for diagonal. And diagonal matrices are really easy to calculate with. So what we would like to do is we would like to go this way. By the way, I believe that is a P inverse. P inverse would go there. We'd multiply by the matrix D. Then we would multiply by P, where P is my change of basis matrix. And then we'd have it. So change of basis matrix, diagonal multiplication, change of basis matrix back. Sometimes that's easier than trying to deal with my A by itself. Okay? So that's the idea there. Now, the other thing that you should remember, by the way, you'll notice the what we're doing here is in order from right to left. So if we're taking we're replacing a times multiplying a vector x with basically 3 matrix multiplications. And that might seem like a lot, but again, sometimes that's going to be a lot nicer to deal with, especially when we're dealing with programming computers and things like that. So that's the idea. Vector a times x is going to be replaced by these 3 matrix multiplications times vector x. And notice that again, p inverse is the first time you hit it, then the diagonal, then p. Now, if we can find a change of basis matrix P where D is diagonal, therefore B is the basis formed by the columns of P, then the D can be that B matrix for the transformation, and we'd have a diagonal matrix, B matrix for the transformation. And this all harkens back to the diagonalization theorem that we just saw in section 5.3. Can we find this change of basis? Can we find the appropriate basis? Well, we can if and only if A has n linearly independent eigenvectors. Moreover, if we can find such eigenvectors, then those eigenvectors form the columns of P, and the eigenvalues are the diagonal entries of our diagonal matrix D. All right. So we saw this earlier. So I want you to go ahead and find a basis with the property that the transformation with respect to that basis is diagonalizable or is diagonal. Maybe I should say it that way. The transformation with respect to the basis is diagonal. And let's let A be this matrix here. Go ahead and push pause and try to find the basis and the diagonal matrix. All right, so hopefully you went ahead and did that. So we start with this matrix A, 3, 2, 6, -1. In order to find eigenvectors and eigenvalues, we start out with looking at A minus lambda I, so that's 3 minus lambda, 2, 6, -1 minus lambda. We're going to take the determinant of that. If I take the determinant of this, 3 minus lambda is going to be multiplied times -1 minus lambda. And then we're going to subtract 6 times 2, which is 12. So subtract 12. So that's the determinant. We set that determinant equal to 0 for the characteristic equation, and then simplify it. When you simplify, you should get lambda squared plus 2 lambda minus 15 is equal to 0. Oops, now something's off here. Yes, I think I did that wrong. So, no, I'm sorry. No, I did this wrong. That's what I had my equation right. Didn't have this right. I'm sorry. So 3 times negative lambda is negative 3 lambda. Negative 1 times negative lambda is a positive 1. Negative 3 plus 1 is negative 2. So yes, negative 2 lambda minus 15. That's what we're getting. Okay, so when you factor that, you get lambda minus 5 times lambda plus 3. That means your eigenvalues are -3 and 5. Once we have those, we plug those in for the lambda here. If I plug in -3, you're going to be looking at a plus 3 times the identity. So we're going to be looking at a plus 3 times the identity. We're going to row reduce that. So by the way, a plus 3 times the identity is 6, 2, 6, 2. When you row reduce that, you get 1, 1/3, 0, 0. So you get an eigenvector of -1/3, 1. Okay? So that's your first eigenvector corresponding to lambda equals 3. Excuse me, lambda equals -3. When you look at lambda equals 5, you do a minus 5 lambda, which becomes -2, 2, 6, -6. When you row reduce that, you get 1, -1, 0, 0. So this leads to the eigenvector of 1, 1. So we have our two eigenvectors, -1/3, 1, and 1, 1. That means we're going to use the basis -1/3, 1, 1, 1 when I'm creating my matrix. And so my transformation with respect to this basis B. Now notice that I put the -1/3, 1 first. That corresponds to eigenvalue lambda equals 3, -3. So -3, 0 would be the first column. And since I put 1, 1 as my second eigenvector, that corresponds to eigenvalue lambda equals 5. 0, 5 would have been my second column. Now, by the way, we saw previously in the last chapter that if you would have switched the order, so if you'd have thrown the 1, 1 up front and the 1/3, -1/3, 1 in the second spot, all you would have had to do is switch the order that your basis came in. So you switch the eigenvalues there. So there we go. So my transformation with respect to this basis is 5, 0, 0, -3, and then we're good to go. Now let's do one more of those for good measure. Let's take 5, 3, 6, 0, 2, 9, 0, 0, -1. Obviously, this is a triangular matrix, so the eigenvalues pop out at you. But go ahead and find a basis B with the property that the transformation with respect to basis B is diagonal. All right. Again, there's a little bit, we're not saying that T of B is diagonalizable. We're saying T of B is a diagonal matrix. A is diagonalizable. Hopefully, that won't screw you up too much. So I fixed it on this slide. I don't know what, T of B is diagonal. A is diagonalizable. All right. So here we go. So we take our matrix A. We see that it has 3 different eigenvalues, 5, 2, and -1. That's because it's triangular, so the diagonal entries are the eigenvalues, 5, 2, -1. Now also we know that each each eigenvalue has multiplicity 1, and therefore we know it's going to be diagonalizable. We just need to figure out what that diagonal matrix is. So we're going to row reduce A minus 5I. I did that in my calculator and I get this matrix. That means that x1 is free, x2 and x3 have to be 0. So you get the eigenvector 1, 0, 0, corresponding to eigenvalue 5. When you do A minus 2 times the identity, I got this matrix. So x1 has to be negative 1 times x2. x2 is free. x3 has to be 0. So x3 is 0, and then negative 1, 1. Negative 1, 1, 0 is my eigenvector, corresponding to eigenvalue of 2. Corresponding to eigenvalue of negative 1, well, when I put in negative 1, row reduce it, I get 1, 0, negative 0.5, 0, 1, 3, 0, 0, 0. That means x1 has to be 0.5 times x3. x2 has to be negative 3 times x3. And x3 is a free variable. So you get 0.5, negative 3, 1, corresponding to that. And again, the order matters, but I'm going to put it as 5, 2, negative 1. So my eigenvector, my first one that I'm going to plug in is the 1, 0, 0 eigenvector. My second eigenvector, I'm going to go with the 2, negative 1, 0, 0. Excuse me, negative 1, 1, 0. Excuse me. Sometimes I get tongue-tied there. And then my third eigenvector is 0.5, negative 3, 1. Okay. Now, if I put them in that order, my diagonal matrix that represents my transformation is going to be 5, 2, negative 1 on the diagonal. And obviously, since it's a diagonal matrix, it's going to have zeros elsewhere. So the matrix with respect to the transformation with respect to basis B is 5, 0, 0, 0, 2, 0, 0, 0, negative 1. All right. So the transformation T with respect to this basis is a diagonal basis. There's a diagonal matrix. So there you go. We can figure out when a matrix multiplication is diagonal, all right, or diagonalizable. So now all of this, again, comes back to it all comes back to that basic diagram that we looked at earlier. That transformation one way across the top is parallel to the transformation with basis coordinate vectors along the bottom. All right, so it kind of works in parallel. All right, so that finishes up section 5.4 for us, and next section obviously will be 5.5.